Happening here. So we are live. The guys in the room still cannot see anything, I think. So let's see if something happens now. Hello. Yeah, okay, fantastic. This thing is alive. Okay, so welcome to today's session of the Discrete Maths 2 course, in case you were wondering what course this was. At the beginning of every course session, apart from the first one, because we had not covered any material yet, I like to start by getting our neurons buzzing by looking at some question and trying to answer it. And this question has something to do with the material we covered last time round. So it's going to be a warm-up exercise for what we are going to cover today. And what we are going to cover today is essentially what we were looking at last time round in more detail, namely the recursive definition of structures of objects in computer science, the recursive definition of operations, functions to operate on these objects, and then what we will see today, and that's the new thing, we will also see how we can actually go about proving properties of the objects and of the functions that we recursively define by using a word, a proof technique that you all know and love. Well, you all know, perhaps you don't love it, but let's see what happens, which is called induction. The big I. Yes, people are just screaming with happiness in here, as you're doing at home. It so happens that I have an alter ego for this course. It's a guy called Dr. X, and he always asks me a question, which I like to relay to the students. So there you are. Here's a question from Dr. X. There are actually two. One of them I will ask later on as a warm-up for the second half of the course, of this course session. Last time we defined the collection of binary lists using a recursive definition. We said, okay, the empty list is a binary list, and then we gave some formation rule, namely the formation rule that you see repeated over there, that tells us how to construct a longer list from a list that we've already built. Now, Dr. X is a very minimalistic guy. He says, okay, why do we need the first condition? Why do we need the empty list is a list? Why can't we just do with the second item in our definition from last time around and say, okay, if somebody gives you a list for your birthday, then this is how you can make it longer, by sticking a bit in front of it. And this bit, of course, can be a 0 or a 1. Okay, would this be a good, honest-to-God recursive definition of the data type of binary lists? If yes, then we can just as well use the shorter definition that Dr. X is providing, instead of the slightly longer one that we used last time around. So what is it that we are defining with just this single definition? Nothing. That's what one of your colleagues is saying. We are defining a very useful data type that contains no objects whatsoever. We are defining the empty set, which is pretty boring, but yes, we are defining that, but it's not what we meant to define. Why? Because if we remove the base case of our recursive definition that says, okay, here's a binary list, and it's the empty one. Then, if we only have construction rules like this one, these construction rules only work if somebody gives you a list to start with. The rule says, if L is a list, then this other thing that you build is a list. But if you don't have any list to start the construction, you cannot construct anything, which means you construct the empty set of things. So this doesn't work. What is the lesson that we learn from this? Whenever, from this example and this question, whenever you're defining something recursively, and this something could be a collection of objects, a data type, a function operating over objects of a data type, thou shall always have a base case, at least one. Of course, you all know this, but it's easy to forget it. It's easy. That's why I'm sort of making you warm up by refreshing your memory. In fact, this is a question that I already asked you in our previous course session, and people said, yes, you cannot construct anything at all, so you can construct nothing. Okay? This doesn't mean you're not defining a set. You're defining a set, but it's the empty one. It's a good set, but it's pretty boring. You cannot, there's nothing in it. Any doubt about this? Excellent. So let's go back to where we were. You might recall that the last thing we did before going to do whatever else we were going to do last Tuesday after the course session, the last thing we did was to define a recursive function, namely a function count that has two arguments. The first argument is a bit, the second argument is a binary list, that counted the number of occurrences of the first argument be in the list L. We defined that recursively, and in fact, I'm going to show you again the definition later on, because we are going to need it when we start proving stuff. Now, what I want you to do for me is to define another recursive function that operates over binary lists. This function is called search for some stupid reason. It takes as input a binary list, and it returns a Boolean. So the type of this function is function from binary lists to Booleans. Now, what should this function return? If it takes as input a binary list L, it should return true if and only if the list L contains two zeros in a row. Or in other words, it contains the list 0, 0 as a sublist. So what you want this function search to do is to scan the list L, and if it finds anywhere two zeros in a row, it will return true. Otherwise, it will return false. Okay, is this clear? This is what you want to do. Because you're doing it, I'm actually helping you if you need any help. Okay, in fact, I'm already helping you by giving a template for a possible solution. In this case, we are going to need two base cases. Why? Well, because there are at least two cases in which the answer is obvious. We are looking for the pattern 0, 0 in the list. Okay, so what your colleague here is saying is that, okay, it cannot happen if the list is either empty or it's of length 1. Why? Because you're looking for 0, 0, the list must have at least length 2, otherwise there is no way you can find two zeros in a row. That's why you need sort of two base cases. And then you will have an inductive step that tells you what happens if the list is of length 2 or more. If the list is of length 2 or more, then it starts with 2 bits, this B1 and this B2, and then this followed by some list L. Okay? Now, that's the template for the solution. You fill it in, and I'm going to write what you suggest I write. Now, let's see if the writing tool actually works now, because before it was not particularly responsive. So there we are. Okay, so what was the pattern? The pattern for the solution I suggested was that we would first define the base cases, and in fact, we've already figured out what the answer should be. So it should be false in both cases. Now, one of the beautiful things is that writing is different in M101 from V101. I actually prefer V101, but it's a smaller room. So long as we are many, on Thursdays we'll be in here. Okay, So there you are. We've done the two base cases. Now I would like your input on how we could proceed to define the result of applying search to a list that starts B1, followed by B2, followed by L, where B1 and B2 are 2 bits. And L is a list of bits. Okay, so what are the possibilities here? B1 is equal to B2 and is equal to 0. In this case, what is it that we want to return? True, because we found right at the beginning of the list, we find the pattern that we were looking for. Splendid. Comment, good start. Okay, well, if the list doesn't start 0, 0, how can it start? Okay, there are 3 other possibilities. Okay, so let's assume that actually B1 is 1. So where is the pattern 0, 0 if it occurs at all? Farther down the list. And farther down the list means, in this case, in the rest of the list, which is actually smaller than the list we start from because it has 1 fewer element. So it's safe to call recursively search on the list that starts B2 followed by L, because we are getting smaller. Never call a function recursively or something which is not smaller than the input you got in the first place. Search B2, that's a 2 there, followed by L. Okay, so what is the other possibility? The other possibility is that, well, no, there's not a possibility. We've done what we wanted. There's the eraser. Well, no, there is actually another possibility. Sorry. The other possibility is that B1 is actually 0 and B2 is actually 1. That's the other possibility. So in this case, where is the pattern that we are looking for if it occurs at all in the original list? Farther down the list, but now where is farther down the list? In Strjál, absolutely. Because now B2 is actually 1, so the pattern 0, 0 cannot start from there. Okay, so your colleague is saying, why can't we make it simpler? So in particular, so if the first 2 bits in the list are not both 0, then you always search B2L. That's what your colleague is saying. Would it work? Yes, it would work. Yes, it would work. You can make it simpler. Question is that I got is, isn't this to get a faster search in some specific cases? Yes, but both solutions are correct. Okay, well, as you know, you want to solve an algorithmic problem, you can write many different programs that all solve that problem. They're all correct. They're just not the same, exactly the same. So whenever there is no single correct solution in general. Excellent. So we have written another recursive function over lists that does something. I'm not saying it's a particularly interesting solving a particularly interesting algorithmic problem. It's just a good exercise for us. Excellent. So what is it that we've done so far? We have defined a data type, in our specific case, the collection of binary lists recursively. We've defined some number of functions over this data type recursively by following the structure of the definition of objects of type binary list. A third thing that we might want to do now is, for instance, to prove properties of the objects that we've defined and of the functions over these objects that we have defined. For instance, you might want to prove that the two versions of the search function that we mentioned before always return the same result for all lists. They solve the same problem. They do the same thing. They have the same input-output behavior as function. Here's another example of a property that we might expect to be able to prove, because if we've done things right, it should hold. This property says that, okay, so remember, or you don't need to remember, we're going to write it afterwards. We define the length function over lists that measures how many elements are in a list L. We've defined the count function that counts the number of occurrences of some bit in the list L. Now, what I might expect is that for every list L that we might care to consider, the length of the list is actually equal to the number of occurrences of the bit 0 in it plus the number of occurrences of the bit 1 in it. This sounds like a very reasonable property, connecting the function length with the function count. Why? Well, because L is a list of bits. The bits are either 0 or 1, so the overall length is the number of occurrences of 0 plus the number of occurrences of 1. There cannot be anything else in the list. Okay, so can we prove such a thing? Of course we can, otherwise we will stop the lecture here. But it's not so much that we can prove this thing, it's more how we go about doing that. So how do we prove it? And that's another one of the joys of recursion. Not only you can give very clean definitions of objects, very clean definitions of functions, operations over objects, but as soon as you've given a recursive definition of a data type, you automatically get from that definition a proof principle to show properties of objects of the data type. And that proof principle is nothing but induction. But it's not like induction on the natural numbers, complete induction, full induction, whatever you call it. It's something that is even more fundamental in computer science, and it's something that is called structural induction. I'll come to the question in a second. It's called structural induction because it mimics the structure of the definition of objects of the data type that you're working with. There is a question. Okay, the question is, what is this statement PL? Is it referring to the thing that we want to prove in this specific case? Yes. But that's just a specific instance of a more general scenario. Okay, because you might want to prove many different types of properties over lists. That's just one property. In general, so let's look at the definition. So let's look first at a concrete example. We'll see several concrete examples, and then from that, you will be able to understand the general pattern. Okay, some people prefer to do very general things to begin with. I prefer to do examples. From the examples, you can understand the general pattern. I can also do it the other way around if you prefer. You prefer examples first and then abstraction later, or abstraction first and then examples? Examples first. That's what I thought. That's why I do it this way. Okay, so what is the principle of structural induction for binary lists? Well, remember, how did we define binary lists? we said the empty list is a binary list, and then we gave a recipe for constructing longer lists from lists that we had already built. You just stick a bit at the beginning of the list that you've already built. This is essentially a counterpart of the definition of the natural numbers. How do you define the natural numbers? You say, okay, 0 is a natural number, and then you say, if somebody gives you a natural number, you can build another one by adding 1 to it. Base case, construction rule. Now, what was the principle of induction for the natural numbers? Since you know that all the natural numbers are either 0 or are of the form n plus 1 for some n that you already built, to prove a property of natural numbers, you first show that it's true for 0, then you assume that it's true for n, and under this assumption, you prove that it's true for the following number, n plus 1. Well, the principle of structural induction for lists is essentially the same thing. You want to show that some statement, for instance, the one on the slide, but it could be any statement whatsoever about the lists that you care about, that you want to prove. You want to show that it's true for all lists. What do you need to do that? Well, first of all, since it has to be true for all lists, it has to be true for the empty list. That's the base case. Second, you do the inductive step. Now, what is the inductive step here? You assume that the statement, I'll take your question in a second. Let me clear this one. You assume that the statement is true for L, for some list L that you've already built. And under this assumption, you show that it's true for longer lists. Lists of the form 0 followed by L, 1 followed by L. If you can do these two things, you show the base case and the inductive step, then you know that the statement is true for all lists. Why? Because any list is constructed by starting from the empty list and sticking bits in front of it, one after the other. Just like any natural number is constructed by starting from 0 and adding 1, 1, 1, 1, 1 sufficiently many times to 0. There was a question or a remark in the second one. Hi, sorry, you had a question or a remark or a comment or... Oh, okay, sorry. So your colleague was just about to say exactly the same that I just said. I should have let him say that. I apologize. Absolutely. Okay, so the best way to understand this proof principle is to prove something with it. And well, we already have an example of one thing that we might want to prove, namely this statement over here that relates the length function and the count function. So why don't we do it? Just like the Nike advertisement, just do it. Okay, yeah, let's do it. So in order to prove statements of the length function of the count function, let me remind you of how these things were defined. Okay, so length was defined as follows. The length of the empty list is 0. The length of a list that starts with a bit B followed by L is, surprise, surprise, 1 plus the length of the rest of the list. Okay, so that's one thing. Now, I suppose I better give myself a little bit more space for writing the count function. Okay, so count the number of occurrences of the bit B in the empty list is 0. That's what we figured out last time around. If you have an empty list, there's nothing in it. And the second case was count the number of occurrences of B in a list that starts with some bit B prime and is followed by L. Now, what is this? There are several possibilities. If B is the same as B prime, then we found one occurrence of B in our list. So the result is going to be 1 plus the number of times that B occurs in L. We unleash the power of recursion and we get the number of occurrences of B in L for free. We just need to add 1 to it. The other possibility is that B is actually not the same as B prime, in which case, how many times does B occur in B prime followed by L? How do we find that out? Where are the occurrences of B in this list? They must be in L, because B is not the same as B prime. So the first element doesn't count. We just run recursively our function on the rest of the list. Now let's be tidy for once. So these are the definitions. Yes, I am. Why is that? Oh yeah, so the question was whether I was recording this question, this session, and yes, I am. Or I hope so, at least. I hope so. So far, so good. Now, what is it that we wanted to prove? What is our statement, PL, where P stands for properties of the list L? Well, the statement that we want to show, that's our version of PL, is just the following one. The length for every L, it should be the case that the length of L is the number of times that the bit 0 occurs in L, plus the number of times that the list 1, that the bit 1 occurs in the list L. So this is actually the statement that we want to show is true for all lists. Okay. So let's do it. What does the principle of structural induction for lists tell us? Well, in order to show that this statement is true for all lists, we got to prove, first of all, that it's true for the empty list, so when L is empty. And second, we prove that it's true for a composite list under the assumption that it's true for the shorter sublist. Base case and inductive step. Let's do it. Base case. The list L is actually empty. In this case, we can just calculate, can't we? We just plug in the empty list instead of L on the left-hand side and the right-hand side of this equation here, and we see whether we get the same result. Okay, so what is the length of the empty list? It's 0. We don't need to guess. It's just a base case of the definition of length. What is count B of the empty list? No matter what B is, it's 0. So length L evaluates to 0 when L is the empty list. Count 0 of the empty list is 0. Count 1 of the empty list is 0. So 0 plus 0 is 0. We are done. Ding. Squeaky bumps? No, not yet. That's the easy part. We just need to calculate. Have I lost anyone out there? Come on, there is a lot of intelligent life in the universe out there. The only non-intelligent life is here. Out there, the universe is empty of very bright people. Okay, so all we need to do is to calculate here. You just plug in the empty list instead of L, and you calculate, and you get 0 on both sides. Now, how about the inductive case? That's where I get confused personally sometimes. So that's where I need your help. Okay, so inductive step. How does this progress? I assume that what I want to prove is true for some list L prime. So I assume that the length of L prime is equal to count 0 L prime plus count 1 of L prime. That's my inductive assumption. Let me call it IA. Oh, the list L prime can be arbitrarily long. It doesn't have to be on length 1. What I want to show is that under this assumption, what I want to prove now is that the length of, say, 0 followed by L prime is actually equal to count 0 in 0 L prime plus count 1 in 0. What's that? This thing is alive. I didn't mean it to be alive. Okay. What are these 3 stars? It's yeah. Where is the delete? Yeah. Okay. 0 L prime. Then one would need to do also construct this proof for the case where the list starts with 1. But let me just do one of the cases. Okay, now I would like to expand this page, if possible. Bottom of the page, expand page, absolutely, fantastic. I'm blind, apart from other things. Thank you very much, whoever you are, much appreciated. Okay, so remember how you prove things about the natural number. What was that? Okay, remember how you prove inductive steps of inductive properties, so you improve by induction over the natural numbers. You assume that the property you want to prove is true for n, you prove it for n plus 1. Here, we assume that it's true for some list L prime. We prove that it's true for a list that you obtain by sticking a bit in front of L prime. Okay, so this is my inductive assumption. It's not an Acronis football club or something like this. It's inductive assumption. And this is what I want to prove. How do I prove it? Well, I calculate using the definition of length and count. So let's do it. What is length of 0 followed by L prime? Don't think, you just use the definition of length. It's 1 plus the length of L prime. So far, so good. Any doubt? If you have doubts, scream now. That's just the definition. That's just the definition of the function length. Let me scroll up. That's how we define it. I'm just applying the definition of the function length. Is that clear? Good. Okay, so now look at this thing. This is actually equal to this. So I can use the inductive hypothesis to figure out that actually this length of L prime is equal to this expression here. I'm assuming it to be so, so I can just substitute equals for equals. So this is actually 1 plus count 0 L prime plus count 1 L prime. This is by the induction assumption, the inductive hypothesis. I'm just substituting equals for equals. Convinced? If not, scream now. In any event, the best way to understand this is to do it yourself at home. But you see, I'm assuming that the length of L prime is equal to this expression. So whenever I see length of L prime, by induction, I can substitute for it what I'm assuming it's equal to. And this is just what I did. Okay, what now? Well, look at this list. What is this expression here equal to? Isn't it the number of times that the bit 0 occurs in the list 0 followed by L prime? Because the number of times that 0 occurs in the list 0 followed by L prime is 1 plus the number of times that 0 occurs in the list L prime. So actually, by definition of count, this is equal to count the number of zeros, the number of times a 0 occurs in 0 L prime, plus count 1 L prime. What I've just done is to replace the underlined bit of the expression that I had before with something which is equal to it by definition of count. And now we are nearly there. Why? Because look at what I want to prove. I want to prove this thing here. And the expression I have so far, length 0 L prime equals count 0, 0 L prime plus this thing here, is nearly equal to it. The only thing that I need to take care of is this expression here. I want to transform this into this thing here. But absolutely. So the number of times that 1 occurs in 0 L prime is just equal to the number of times that it occurs in L prime. Because 0 L prime starts with a 0, so the 0 is not equal to 1. It doesn't add anything to the number of times that 1 occurs to it. So I'm done. Bingo. You did it. You just proved the first statement about lists using structural induction. Your life will not be the same again. This is the first day of the rest of your lives. This was a mantra in American Beauty, a movie that was fairly popular a long time ago. Now, of course, this was not quite going to the gym. I was sort of showing you how to do this exercise, but you can do it much better than me, provided you practice a little bit. And that's what we will be doing, even though most of your practice will be in defining stuff rather than proving a lot of properties about it by induction. But remember, the important thing is that in principle, if you really need to, and if you really want to, you can prove properties of your recursively defined objects using structural induction. And we will see several other examples of these proof principle at work. Okay, now it's time for a break because you've done a lot of work, so you need a little bit of a break, a 10 minutes break. Before we break, any questions? Okay, 10 minutes break, and then we reconvene.